Hello, everyone. Welcome to Scaling Python with Dask. We're going to get started in just a few minutes. We're going to let people register here and get settled. So stay tuned. We'll get started in about a minute and a half. Hello, everyone, and welcome to Scaling Python with Dask. My name is Gus Kavanaugh, and alongside of Chastity uses webinar software like a DJ Gibson, we're going to be your moderators for today. So we're really excited. We're going to introduce Matt here in a second, but first of all, just some ground rules. I hope you brought a lot of curiosity around scaling Python or how to use Python with large data sets. Please fire your questions away into the question box and go to webinar. Those questions will come just to the moderator, so they won't be global, and we'll do our best to answer them on the fly. Any questions we don't get to during the webinar, or if there are questions that we're seeing lots of groups of, or even if they're just especially poignant, we're going to offer those up to Matt at the end. And if we don't get to it either during the webinar or at the end live on air, we will make sure to follow up with you via email. But please do reach out to us fast and furiously. We're really excited to hear from you all. So with that, I'd like to introduce Matt Rocklin. So Matt Rocklin is the core contributor of the Dask project, along with a bunch of other things in the PyData ecosystem. He holds a PhD in computer science from the University of Chicago, and he's all in all a really smart guy. So I'm very, very excited about this webinar. I think you're going to get a lot out of it. And if you are somebody who has a little bit of data, has a lot of data, is not necessarily that interested in getting into the JVM, this is really the webinar for you. So with that, I will pass it over to Matt. Please take it away. One second. Looks like we're having a little microphone trouble here.
Hello, everyone, and thank you for coming to Anaconda's webinar, Scaling Python with Dask. My name is Matthew Rocklin. I'm a core contributor to Dask. I'll be walking you through the project today. Dask is a library for parallel computing in Python. It was designed to scale other libraries like NumPy, Pandas, and scikit-learn, and scale them to work on multi-core laptops or up to large 1,000-node clusters. Before we understand Dask, we first need to understand the foundations of the numerical Python ecosystem. The numeric Python ecosystem is composed of many independent packages, some of which you may know, like array computing with NumPy, or tabular or data frame computing with Pandas, machine learning with scikit-learn, or user interaction with Jupyter. These popular packages form the foundation of a full ecosystem of packages that includes thousands of other libraries for natural language processing, visualization, networking, mathematics, etc. These libraries are developed independently by people around the world, but they form a cohesive whole as an ecosystem that operates together. This ecosystem is very popular today for a few reasons. One, it's easy to use. It was designed with students and scientists in mind, and so is popular in education, in boot camps. It's very easy to find people who know Python today and can use these packages. It's also very fast. Many of these packages are written at a low level in C, C++, Fortran, or CUDA, very efficient languages. They're also fast because they use sophisticated algorithms. Many of the authors of these packages are researchers at the forefront of their field, using sophisticated algorithms that make things asymptotically faster. Because this ecosystem is both easy to use and fast, it gets applied across a wide set of industries. And so, if there's something you're looking to do, it's quite likely there's already a package that solves your problem. Unfortunately, the ecosystem also has some weaknesses. Libraries like NumPy and Pandas were largely designed to work on in-memory data, that is, data sets that fit in the RAM of a single machine. They're also designed to run single core, meaning on a single thread that fits in a single CPU on a single machine. This is fine for 99% of use cases. The vast majority of analysis today runs on data that is small enough to fit on a single machine. Still, sometimes some problems do scale out larger than that. And our goal is to help the whole ecosystem scale. Dask's role here is to complement the existing ecosystem by adding a single package that allows everything else to evolve towards scalability. So our goal is to have libraries like NumPy, Pandas, and scikit-learn, and all of the other packages in the ecosystem scale to work on larger than memory data, using either multi-core parallelism on a single machine or distributed parallelism across a cluster of many machines. Dask's goal is not to replace the ecosystem, but instead to complement it and allow other packages to evolve. So again, Dask is a library to parallelize other libraries like NumPy, Pandas, and scikit-learn and scale them from personal multi-core workstations to large distributed clusters. Because it was designed to scale other libraries, it also ends up being very useful to scale other custom codes. So a lot of that use of Dask today is not using parallel pandas or parallel NumPy, but instead using it to parallelize in-house custom systems. So in this webinar, we're going to explore both parts of Dask. We're going to start off talking about how to use Dask's parallel versions of NumPy and Pandas to do scalable workloads that look very similar to using NumPy and Pandas, as we're working at a high level. Then we're going to dive a little bit more deeply, look at how to use Dask at a low level to parallelize custom code. We'll talk a little bit about dynamic task scheduling, which is how Dask does all of this work. We're going to start with the Dask data frame. So Dask data frame is a scalable implementation of the Pandas API. So Pandas is a popular project for tabular analysis, such as you might use to parse and analyze the data from a CSV file. So this data must fit in memory with Pandas, but with Dask data frame, we'll give you the same API, but operate on larger data sets. So here we're seeing the Dask data frame API. We're reading not a single file, but many files. Here coming from Amazon's S3 in the cloud, but it could be coming from the Hadoop file system, the network file system, or any other big data storage technique. The API is very similar, you'll notice, and this follows through with most of the Pandas API, including reductions, group by, joins, time series, rolling operations, resampling, etc. Dask data frame is evolved with the Pandas project. It's actually built by some of the Pandas maintainers. So the API compatibility is really thoroughly tested. Internally, Dask data frame is just many small Pandas data frames coordinated by Dask. So for example, imagine the picture on the right. Imagine you have a long time series that's too large to fit in memory on a single computer. But you might break up that time series, say by month, and put those on different computers, each in an individual Pandas data frame. So those Pandas data frames will now be coordinated by a single large Dask data frame, which will provide sort of a logical orientation around all of them. When you do an operation on a Dask data frame, it will translate into many operations on all the smaller constituent pandas data frames. In this way, Dask data frame has reused a lot of the same internal computation of pandas and gets a lot of the same speed that pandas gets. Additionally, because it's just using pandas under the hood, a lot of existing code is very easy to make work with Dask data frame. So again, Dask data frame provides the pandas API as a front end, but also uses pandas under the hood to make things nice and efficient. Similarly, there's Dask array. So Dask array does the same thing, but with NumPy, the NumPy n-dimensional array. So on the right, you can see that one Dask array is just a logical coordination of many smaller NumPy arrays that might either be living on disk if you're on a single machine, or living across distributed memory if you're working in a cluster. Dask array provides a large subset of the NumPy API, so that you can do your normal linear algebra operations, reductions, slicing, overlapping computations happily with the NumPy API, but now operating in parallel. Again, either using many cores on a single computer or many machines across a cluster. So we're about to see an example using Dask data frame on a cluster to do a pandas-like operation spread across many machines in the cloud. So to see Dask in action, we're going to leave this slideshow a little bit and move over here where we have a Jupyter Notebook running in the cloud. So this notebook shows off using Dask data frame to read some CSV data from Google Cloud Storage. Google Cloud Storage is a lot like Amazon's S3, like the Hadoop file system on premises. So here I'm going to connect and look at a few CSV files that I have living on the cloud. This is the New York City taxi cab dataset showing every cab ride for the city for the year of 2015. I'm going to use the pandas library to read a few rows of that data. Unfortunately, I can't fit all of it in memory at once. This data set is around 20 gigabytes on disk or around 40 or 50 gigabytes in RAM. Not huge, but definitely bigger than I want to put in a single machine. So here I'm using the pandas read CSV function, reading just a few rows, just to get a sense of what the data looks like. Every row corresponds to one cab ride in the city of New York. And we can see when the cab was picked up, when they were dropped off, how many passengers there were, where the ride happened, some more columns breaking down the fare. How much was the tip, how much were taxes, etc. So while I don't happen to have enough memory on this particular machine to load this data, I do happen to have a cluster nearby. So I'm going to connect to that cluster using Dask. You see I have 16 workers, each worker has 4 cores, there's around 200 gigabytes of RAM total, more than enough for this 50 gigabyte data set. I happen to have the dashboard open over here, so let's go and take a look. So on the right, we're seeing the Dask dashboard in the workers pane. We see there's 16 workers, each worker has 4 cores, and they're not doing a whole lot right now. Let's give them something to do. So we will use Dask data frame to load that data from Google Cloud Storage. And what that's going to do is that's going to break up those 12 CSV files into a few hundred blocks of bytes. Each of those blocks of bytes will then be read by pandas read CSV, creating a pandas data frame in memory on one of our workers. So you're seeing here on the right the activity of each of our cores. The light green color here corresponds to reading a block of bytes, and then the dark green corresponds to parsing those bytes with pandas read CSV. Every line corresponds to the activity of a single core on our 64 core cluster. So you're seeing here that they're alternating between reading data and parsing that data. They're making good progress. The object we get back from that is similar to a pandas data frame. It's a Dask data frame. This object is going to provide a lazy version of the pandas API that will then coordinate to all of our now 300-ish pandas data frames sitting in memory on our cluster. So let's go ahead and look at that data frame. We can inspect to see what the D types were, see all the columns that were present. We can look at a little bit of the data. And we see that it looks very similar to the data set we had before. This is just showing all of the various columns of our data, much as pandas would. Because again, this is just a bunch of pandas data frames in memory throughout our cluster. We might do something simple to this Dask data frame, like compute the length. And this will compute the length of all the individual pandas data frames, and then sum those lengths together and give us the sum, telling us that there are 150 million rides in total for this year. We can look over here on the right, and we can see how Dask broke that down. So on the left here, looks like these are all the individual length computations on the smaller pandas data frames. We can zoom in here a little bit and see how long they took. So these are quite fast. These are taking, 20 microseconds. That's not taking much time at all. All those lengths finish in, 20 milliseconds. We then communicate all those intermediate results to one machine. Red is communication. It takes another 20 milliseconds or so. And we aggregate all of their sums. So this is sort of a classic MapReduce style algorithm to produce the length of many smaller pandas data frames. But the user didn't have to think about how to break it down. They just called length. Let's look at a more complex example that'll go a little bit beyond sort of MapReduce style algorithms. Let's see how well New Yorkers tip based on the hour of the day. So we're going to see how well riders tip, maybe 20% at noon, 10% in the evening. We're going to get some of that information. Before we do that, though, we need to clean our data a little bit. So here we're going to remove some bad rows. Turns out there were some free rides in the city of New York. We're going to make a new column, the tip fraction. This is going to be the ratio of the tip amount to the fare amount. Was it a 10% tip or 20% tip? If you're familiar with the Pandas API, this should all look pretty familiar to you. It's the exact same. Then we'll do some more time series operations. We'll group by the day of the week, by the hour of the day, and then compute the average of the tip fraction. Again, this is just the same Pandas API that you should ideally be familiar with. And what Dask will do is it will break down that high-level operation into thousands of smaller Python functions that they need to run on all of our Pandas data frames. And we're seeing that again on the right. Let's run that again just to see what happens. So you're seeing all the different colored bars happen, and each individual colored bar corresponds to one Python function running on one of our threads on one of our workers. That finished around 6 seconds. And we get the result. So it looks like New Yorkers tip pretty generously. It's around 24, 25% on average, with a very curious spike here at 4 a.m. It gets up to about 38% on average. I asked my colleagues in New York, they say this is probably last call at the bars. So what we've seen here is two things. At a high level, we've seen that Dask data frame provides a pandas-like experience, but on larger data that's distributed across a cluster. So if you're familiar with pandas and you like pandas, you can now scale your analyses onto larger data sets. Here we've done, with the data set that's 50 gigabytes large, but people use Dask with 100 terabyte data sets routinely. On another lower level, we also saw how Dask broke down a high-level query, like this group by aggregation, into thousands of small Python functions that had to run across a cluster. So that's getting sort of more into the core of Dask. Let's look at that a little bit more closely. So let's look at all the tasks we've run so far. So this is showing a more historical view of what we've done. And let's go and look at our last two computations. So if you recall, we ran the same computation twice, and that's showing up here. Let's just zoom into one of them. So here we're seeing the activity. Recall that every line here corresponds to one thread of our cluster. We've got 64 cores on our cluster, and what they were doing over time. Different colored boxes correspond to different kinds of computations. Looks like this light green is a series group by count chunk operation. And the red boxes correspond to overlapping communication. So this high-level query was translated into many, many small Python functions that had to run in parallel across our cluster, and Dask handled that for us. And how it did that, let's look at this data in a different view. It did that by constructing a task graph. So this is all internal. You don't need to understand this in order to know how Dask works, but this query that we just ran is represented in Dask as this task graph, where every box here corresponds to one Python function that has to run by some machine on our cluster. So it's Dask's job to both construct this graph and then execute it in parallel. Let's run that computation again, and we'll see it run in parallel. So it's a little stuttery. There's a fair number of tasks running here. But you got to see Dask walk through this graph executing things to release all of this data, and there's just this one tiny result left in memory. So that shows you a little bit how Dask works internally, and we're going to get into that in the next section. But again, I want to sort of go back here. So you don't need to understand how the task graph stuff works. From a high level, the projects like Dask Data Frame give you a pandas-like API that works across a cluster. There's similar APIs for NumPy arrays or for scikit-learn or other projects that are starting to use Dask internally. Generally speaking, they provide a similar API to what they used for in-memory computation, and they reuse the in-memory computation, but now distributed across the cluster. Okay, let's go back to the slides and let's dive in a little bit into the more lower-level parts of how Dask worked. Most people are originally attracted to Dask through the parallel implementations of pandas and NumPy, like Dask data frame. However, what we quickly find is that about half of them eventually start using Dask core. So let's talk a little bit about that, and you may be in one of those halves. So often you want to use Dask to parallelize custom Python code. So when we first made Dask, we built things like Dask array and Dask data frame, and we assumed that everyone would be using them. However, what we found is that when we approached different problems with these big arrays of big data frames, we found that they didn't always fit. People often had parallelizable code that had lots of opportunities for parallelism, but wasn't just a big array or big data frame, it was something more complex. So what we found is that even though the parallel algorithms in Dask and Dask data frame weren't as useful, the internal structure of Dask, the task scheduler, which we'll get to in a moment, was very useful. So let's take a step back for a moment and let's look at this code sample. We have a couple of for loops that are nested. We're iterating over a couple of collections. And then based on some condition, we're calling either F or G. This code is parallelizable. There's lots of opportunities to make this run faster by calling F and G many times in parallel. However, it's not quite clear how to rewrite this code to be a big collection, like a big Dask data frame or a big array. Also, we don't necessarily want to rewrite this code. It's kind of clear as is. People who wrote this might want to keep it the same while still getting parallelism out of it. So the question is, how do we parallelize more code like this? That tends to be pretty common in in-house custom business logic. So let's look at a simpler example. We have a couple of small functions here, increment and add. Increment adds 1 to a number, add adds two numbers together. And we want to call increment twice on 1 and 2, and then add the results together. We might represent this computation as this graph here to the right. So we can see here there's opportunities for parallelism. Increment, we can run both at the same time. Then we need to wait until both of them finish and then call add. As written, Python won't do this. Python will just run through them and run them sequentially, one at a time. But we would like to get that parallelism. Here we're using simple functions, increment and add, but you might throw in here your own functions for loading data or cleaning data, or maybe doing some machine learning operations. So Dask provides an API, Dask delayed, which you can use to annotate functions to make them lazy, to make them build up these task graphs for you. So the task graph here to the right is constructed now by these lazy versions inc and add. So when inc and add run, when I call them on inputs, they don't actually execute the function. Instead, they take that function evaluation and they store it for later use, and they return it inside this delayed value C. Now, if I call compute on C, then a bunch of parallel computing will kick in and it will run through this graph in parallel across parallel hardware. It might be a local thread pool on my laptop, or it might be a cluster. So using tools like Dask delayed, you can write normal Python code and make it parallelized. So looking back at our example before with this nested for loop, you can construct task graphs similar to what's on the right out of sort of normal looking Python code. This is really useful in a lot of situations. It really removes a lot of barriers to parallelism. It allows parallelism to be used more broadly. You don't only need to wait until you have a big data frame or a big array to go parallel. You can use parallelism everywhere throughout your code base. This allows a lot more everyday use of the cluster inside your institution. It also allows for you to use parallelism without as much rewriting. So there are two challenges here. One is constructing the task graph, which we handle through tools like Dask delayed. The other one is executing that task graph. So here's a trace showing, I think this is a local scheduler running on a single node, walking through a task graph with 4 cores. And so there's sort of what Dask does at a low level. It uses APIs like Dask delayed to construct task graphs. Then it uses Dask schedulers to execute those graphs on parallel hardware. We'll talk about more about those both. First, though, let's switch and see a short example of using Dask delayed and arbitrary task scheduling. Okay, let's move back to the cluster. So I have our new notebook here with the same functions from before, increment and add, but here I've added some random sleeps into them, just to make them simulate some work. And again, you should place into these functions functions that you might use internally, the kind of data you might use, the kind of computations that you might use. We've also added a new one, decrement, which is similar to increment, just subtracts one. So these functions are not yet annotated with Dask delayed, meaning that they're just going to run like normal Python functions. Here I'm going to run them normally, just calling increment and decrement and then add. This will take between 1 and 3 seconds. Here 1.7, here a little bit longer or a little shorter, 1.4. So if I want to run them in parallel, I can use Dask delayed. Here I'll use Dask delayed as a function, just to transform those functions directly. So I'm taking an increment, the original version, and producing a new lazy version of it. Now when I run that same cell, it will run immediately. Whoops, need to run this cell first. So here I run it normally. Now that I've delayed things, it runs immediately, and it returns not a concrete result, but instead a delayed object. That delayed object holds on to all the computations that I've asked it to run here that haven't yet been run. So I'm going to visualize that task graph, and we see that we're asked to call increment and decrement, and both of those produce outputs, these boxes. They're then inputs to another add function. Let's go ahead and run that by calling the compute method. This will actually ask Dask to compute that for us. So this will again run somewhere between 1 and 2 seconds. Now these increment and decrement can happen at the same time. And note that we haven't actually connected to the cluster yet. This is all happening in local threads inside of this Jupyter notebook. So we'll get into this a little bit later, but Dask doesn't need to run on a cluster. Dask can run very comfortably just locally on a single machine. But let's go ahead and connect to our cluster. The same system we had on the right, the same cluster from before. Let's call compute again. Now we call compute is going to use the cluster. So it will call decrement, takes around 500 milliseconds, and increment at the same time on different threads, this took around 700 milliseconds. Then it has to communicate one of those results from one machine to the other. Looks like that took around 9 milliseconds. And then it called add after that. Let's run it again. And so again, it's doing this the same way. So we transitioned easily from running in a local process, just on a local machine in Jupyter, to running on a cluster fairly easily. Let's amp this up a little bit with for loops. So one of the nice things about Dask delayed is very easy to integrate into existing code that just looks like calling functions with for loops, and it captures all of that parallelism for you. So let's go ahead and run that cell. And we can see here on the right that we're using our cluster. We've got these 64 cores, and they're alternating between calling increment and decrement and add for us. And from our Jupyter notebook, we really have all the power of this cluster, or a much larger cluster if we want it. So this is really the power of Dask delayed. It allows you to use normal looking Python code, or normal-ish. Sometimes you have to sprinkle in Dask delayed comments. But you get to run in parallel across a cluster. So beyond just sort of simple for loops, Dask delayed is often used to build more complex logic, or more complex algorithms. For example, let's consider this code. So we have now all of our results of all of our add functions. There's 250 numbers spread around our cluster, and we might want to add them up. We could do that by moving all of those to one machine and then calling sum. Or we might do that a little bit more cleverly by adding them up pairwise. Take every neighboring pair of numbers, add them up, so we now have half as many. Then take all of those pairs and add them up, so we have half as many again. We might continue doing that until we have only one result left. This is called a tree summation. It's commonly implemented in projects like Dask Data Frame or Dask delayed or Spark or SQL databases. Let's say it wasn't though, and we had to implement it ourselves. That code is implemented here in normal Python code. This is a Python code that you need to understand immediately, but it shouldn't look too scary to you. So we have a couple of nested loops, and in the innermost loop, we're taking neighboring elements of all of our numbers, and we're adding up just neighboring elements of them. We're going to keep doing that while there's more than one number. And this Python code implements the tree summation algorithm I just described. Let's go ahead and visualize that. We haven't run it yet. So by calling this delayed add function, we've constructed up a task graph, and we're seeing that task graph visualized here on the bottom. And you can see the tree structure. The structure of the graph we've created with Dask delayed looks actually similar to the diagram that we've produced up here. Let's go ahead and run that on our cluster. And you can see that a variety of add functions are running across our cluster. There's little bits of communication, all these little red boxes, as it's moving intermediate results between machines. And you can see that there's a lot of parallelism at the beginning of the computation and less parallelism towards the end of the computation as we get sort of closer and closer to the top of that tree where there are fewer and fewer tasks to do. Let's go and look at that computation again in the graph mode. This again, just to get a sense for what Dask is doing. So here you're seeing the graph we produced, and we've got one result out. Let's run the computation again. We can see Dask step through that computation as it runs. Let's run that one more time. So as the boxes change color, you can see them move between states of being in memory, red, green is processing, blue is released. They no longer need to be around. And so really at a core level, this is what Dask does. It produces task graphs and executes those graphs in parallel. The magic of systems like Dask delayed is that you can construct these task graphs, or you construct parallel code from normal looking Python code. And this allows you to use Dask and parallel computing more broadly throughout your projects. You don't necessarily only need to use Dask data frame or Dask array. You can use Dask many places throughout your projects. This, incidentally, is how we build projects like Dask delayed, or how we parallelize scikit-learn or other projects like that. But you can do this too. It's very accessible to general computing inside of companies or other organizations. So let's go back to slides, and we'll see a little bit about how Dask executes these task graphs, either on single computers or distributed across a cluster. Now that we've seen those two demonstrations of how Dask can work, at a high level with APIs like Dask data frame, or at a lower level to parallelize custom code with APIs like Dask delayed, let's look a little bit about how Dask actually executes those parallel computations. So in all cases that I just mentioned, Dask APIs eventually produce task graphs. A task graph in this case is pictured in the center here, and every circle here corresponds to some Python function that has to run. It could be any Python function. It might be a pandas function like pandas read CSV, or it might be your own function that you've developed. Every box here corresponds to some Python object that was produced, some data, some intermediate data result. And there might be edges between different nodes here corresponding to data dependencies. So these can be any functions that you want, and it can be any pieces of data that you want. It doesn't need to be pandas data frames or NumPy arrays. It can be your own systems. Now it's the job of the Dask API to produce these task graphs and help users with normal Python syntax produce them. It's the job of a Dask scheduler to execute these task graphs. And this is another challenge entirely. So given a graph like this, which could be representing a big data frame computation, or it could be representing some custom code, how do we execute it in parallel on a certain parallel hardware, be it a local thread or process pool on a single machine, or a distributed cluster living on the cloud? So Dask schedulers solve this problem, and there are roughly two classes of Dask schedulers, those designed to run on a single machine and those designed to run on a cluster. Let's take a little bit of a look at the cluster and then the single machine case. So Dask on a cluster is composed of three different components. At the center, there's the scheduler, and this is doing the job of coordinating everyone else in the cluster. Then there are all of the workers, which are going to be running the computations, sharing data between each other, holding on to intermediate results. And generally speaking, they're the workhorses of this operation. Then there's the clients, and this is us in our Jupyter notebooks or in some automated process that is constructing task graphs and then sending it out to the cluster. You can have many clients connected to the same cluster, and the clients don't necessarily need to be on the same network. Though it is very nice for the scheduler workers to all be the same. So commonly you might have the scheduler workers live on some Hadoop cluster while the clients live on some more data science system like Anaconda Enterprise. So the clients interface with users. They deal with APIs like Dask data frame. The workers do the computation, and the scheduler coordinates everyone together. Now, if there's any IT people in the room, maybe asking about how you set this up. So manually, you should never do this, but manually, when you install Dask, you get a few executables that you can run. One is the Dask scheduler process, and you run that on one of your machines. And then you run the Dask worker process on many other machines, pointing them back to where the scheduler is running. Use that same address of the scheduler to give to your clients, and that's how they connect. In practice, very few people set up Dask this way. There's a variety of automatic tooling for Kubernetes, for Yarn, for traditional high-performance computing schedulers that's available, and you should use that instead. These make it very easy to set up Dask on a variety of clusters from Jupyter Notebooks or from any other system. If you want to learn more about this, I recommend going to the documentation at dask.pydata.org. There's a variety of details about how to set up Dask well. However, most people who use Dask don't use it on a cluster. They might use it on a cluster eventually, but they usually start just on their local laptops, just playing around, or on some Jupyter Notebook in their company that isn't yet connected up. Fortunately, Dask was optimized for this situation. You can start up by Python or Jupyter, you can import Dask, and you can go right ahead and do a lot of Dask computations without ever setting anything up. By default, this will use a local thread pool or local process pool, depending on the kind of computations you're doing. This removes a lot of the barriers to entry. It also is very, very efficient for the common case of moderately large, but not very large data sets. People use Dask on their laptops to handle 100 gigabyte data sets every day, only going to a cluster where they need to do something bigger at sort of the terabyte scale. So this ends up being a lot simpler, and it reduces a lot of the sort of overhead of having to switch to the cluster. That being said, it is pretty easy to switch. Once you've built up some computation you're pretty happy with, you can then scale that out if you want to, just by connecting to a distributed client that connects to a remote cluster. So this makes it very, very easy to switch from prototyping on a laptop, and maybe you stay there, maybe that's enough for you. But if you need to, you can then switch over to using a cluster. And the cost of switching is very, very low. It's not a big cognitive switch to rewrite your code or to set things up. So that's how Dask runs in basic terms on a cluster. We're going to talk about why people might use Dask and why people might not use Dask, what some alternatives are. First, 6 reasons to choose Dask. Reason number 1, familiar APIs. This is the most common reason that people start using Dask. They like NumPy, they like pandas, they like scikit-learn, and they want scalable versions of them. Reason number 2, Dask scales up. It's easy to use on the cloud or on high-performance computers with thousands of machines. People routinely use Dask to manipulate 100 terabyte plus data sets interactively from Jupyter or on automated systems. But Dask also scales down. So Dask is very easy to use from a laptop in a single process and a single thread. You don't need to install or deploy anything heavy. It can be installed just like you can install pandas and imported just like you import pandas. It's very, very lightweight in that way. And this creates a smooth transition from using pandas or NumPy to using Dask data frame or Dask array on a single machine, now to a cluster, and then back down. And because it's all using the same technology under the hood, it's a very, very pleasant experience to move up and down along those scales across architectures. Also, Dask helps solve complex problems. So many people have problems that are highly parallel, but don't fit easily into sort of the big data frame model. The graph we're seeing here is a task graph of a credit risk calculation done by a large retail bank when people apply for credit cards. And so every point you see on this graph is some Python function running some complex model. And the combination of all these things is what they run every time we want to figure out how someone's credit line. This is very clearly parallelizable, but it's not just a big, database query. It's something more complex. And Dask does these sorts of problems very, very well. It's one of the few big data tools to do this sort of problem very, very well. Dask is better at more bespoke or custom systems. Reason number 5, Dask works very, very well with native code. So it's one of the few non-JVM or non-Java virtual machine distributed frameworks. Most big data systems like Hadoop MapReduce, Apache Spark, Apache Flink are written with Java-based technologies like Scala. These create some barriers for code written in languages like C, C++, Fortran, or CUDA to integrate well with those systems. Dask, on the other hand, is written in Python, which has a strong history of interacting with native code. And so if you're using a lot of native code, Dask tends to be a much friendlier way to interact and scale that code across a cluster. And sixth, and finally, Dask is just one part of a much broader ecosystem of projects like NumPy and Pandas scikit-learn, but also thousands of others that are growing rapidly and have a very rich interaction between them. Dask was very much designed to complement this existing system and help it grow. And so people already using this ecosystem will likely find that Dask fits in well to their existing code base. However, there are also some reasons to not choose Dask. There are some alternatives. Let's go through a few of them. There's a multiprocessing module. So the multiprocessing module is very commonly used in the common case of parallelism. We just want to run one function across lots of pieces of data in parallel across different processes. This is very common. It's well understood. If you don't understand it, probably your neighbor does. It has a little bit of weaknesses when you try to handle more complex workloads. Whenever you have data dependencies between tasks, for example. You want to run these 100 functions, and once they're done, you want to run these ones afterwards. Handling that kind of dependency is hard for projects like multiprocessing. You might want to choose something like Dask or another task scheduler like Airflow or Celery. Additionally, you might not want to use processes if you're using NumPy, Pandas, or scikit-learn code, which releases the GIL. Using something like a thread pool will probably be a little bit more efficient. Apache Spark is also a very popular tool and a very strong choice, especially if you're using more SQL-style or database-style queries, or maybe just traditional BI tooling. So if you're doing some ETL, loading in some JSON, doing some data cleaning, doing some SQL queries on that, maybe a little bit of lightweight machine learning, Apache Spark is a good choice. Additionally, it integrates very well into JVM infrastructure. Again, if you're doing a lot of Java tooling, Spark is a great choice for that. It's written in Scala. It'll integrate very well. Spark is also an all-in-one framework. So it's just, you can install one thing and it fits, and that's all you need. There's not a bunch of different packages to manage. And then finally, Spark is also just very well trusted and very broadly deployed. It's generally a safe choice. Weaknesses, however, so while Spark is very, very good at traditional business intelligence applications, it doesn't extend very well beyond those. So if you're doing maybe more advanced machine learning, like deep learning, it's usually not the right choice. If you're dealing with data outside of the tabular data model, if you're looking at complex images or more complex computations, Spark may become a little bit awkward to use. The JVM native code barrier is an issue. So PySpark exists and works very well, but there could be some usability issues and some debugging and performance problems. If you have a lot of native code, it might not be the best choice. Similarly, Apache Spark reinvents its own ecosystem. So if you're used to using other projects like NumPy or like Pandas scikit-learn, you're probably going to be rewriting those systems when you use Spark. And that can be, again, a little bit challenging. You have to train new people. You have to throw away old code bases. It's a little bit awkward to integrate Spark into existing code bases. And then finally, there's MPI. So high performance people in the crowd will know MPI as being the fastest and most flexible distributed system that exists. It's well deployed on high performance computers and is, generally speaking, just the fastest solution around. It's the only real solution if you want to do, million core massive simulations today. That being said, it's hard to use by non-experts. It's not commonly used by data scientists, and it's often overkill for more data science problems. But if you really want the best speed possible, MPI will definitely beat projects like Dask or Spark or really any other project. Finally, let's look at some reasons not to choose Dask. So first, Dask is not a SQL database. We get this question a lot. No, Dask does not parse SQL. It does pandas-like computations very well, but it doesn't do the sort of 100-line or 1,000-line complex SQL query. And if you're that kind of person. If you're that kind of person, you really need a proper SQL database like Postgres or Impala or Spark SQL. Similarly, Dask is not MPI. has overheads around 200 microseconds per task and a few milliseconds of latency. This is very, very fast for most data analysis solutions, but it can be pretty slow if you're trying to deal with 100,000 or million core simulations. Similarly, Dask is not a JVM technology. Dask targets Python and the associated languages around it, like C, C++, and CUDA. But it's not really aiming to support other languages like Java or Scala. If you're using those languages, Dask is not a good choice for you. And then finally, Dask is not always necessary. Or more generally, parallelism is not always necessary. Parallel computing is very popular today. It's big data is a big sexy term, but there are many times when using better algorithms or sampling or changing your storage format or using compiled code like Numba or Cython might give you a much better speed up much more cheaply, both in terms of financial costs and in terms of maintenance. So you may want to look at some other options before you dive into parallelism. It's good to always check that. Finally, let's look at who uses Dask and what kind of applications it tends to be used for. So we see Dask being used by three main groups. There's people who want big pandas data frames. This tends to be the sort of entry point. Most of the questions you read on Stack Overflow are people who are using pandas and want to scale it out to larger data sets and are using Dask data frame to do that. Secondarily, a lot of numeric groups use Dask's n-dimensional arrays. This tends to be people doing maybe more different kinds of data analysis, things like satellite imagery, medical imaging, analyzing simulations like in oil and gas or climate science, and a lot of signals processing. And they really like the fact that there's a scalable ND array, scalable parts. A lot of advanced groups using Dask to implement their own internal systems. This is very common in finance, also operational systems that do data acquisitions or physical hardware devices. And I would say, based on my experience interacting with people, Dask users roughly fall, maybe a third into each of these categories. None of them is particularly dominant. So that ends up creating a good group of people that all push on Dask in different ways and force the project to grow and evolve in a way that seems to support everyone. So finally, I want to also mention some things we didn't talk about, but we could make the subject of future webinars. So we didn't talk at all about scikit-learn and how people use Dask for machine learning. There's a lot of information out there. I encourage you to look at the documentation. Similarly, we didn't talk about array computing or using Dask in more high-performance settings. We also didn't talk about real-time applications. Dask can evolve the computations as they occur, which is very, very useful to handle streaming data, but also operational systems that need to respond to real-world events. We didn't talk at all about performance and scalability. I sort of casually mentioned people use Dask on sort of 100 terabyte data sets on 1,000 node clusters, but we haven't seen any of that yet. That information does exist. I encourage you to look outside on the web. And then finally, we can talk about deploying Dask. There's a lot of interesting tricks you can do about running Dask on your cluster in nice dynamic ways to make it easy to use Dask in your institution, but also be very efficient with the resources that are around. So that's it. Thank you all for coming and for listening to everything. I encourage you to learn more. You should go to dask.pydata.org, so we keep the main documentation. And there's lots of information there, many resources, tutorials, information about how to deploy Dask or install it. There's also documentation about different ways to use Dask. The things I've talked about here may not apply to you. There may be some other way in which you want to use Dask that's different. And there's more documentation there that you can use to tailor your experience a little bit. So I think I'm going to hand it off to Gus for a few minutes, and then we'll have questions at the end. Thank you so much.
Matt, thank you so much. That was fantastic. I hope you all enjoyed that presentation as much as I did. We'd like to give you a little bit of information about where to go next before we jump into Q&A. So if you haven't, go to anaconda.com/distribution and download Anaconda. In addition to 300 plus libraries out of the box, one of those is, or not in addition to, but one of those libraries is Dask. So if you install Anaconda, you'll have Dask. And then, of course, check out the Dask page if you'd like to install it separately. Finally, we haven't touched on this much, but if you would like to use Dask and a number of other Python and R libraries for data science behind your corporate firewall in an enterprise setting we do offer Anaconda Enterprise. And if you would like to test that out for yourself, reach out to ambassador@anaconda.com, and we'll get you set up with a free 30-day test drive of Anaconda Enterprise. So again, if you're doing work individually on your local machine or on a cluster as an individual, check out the Dask project and Anaconda distribution. If you'd like to use Anaconda in an enterprise setting, do check out Anaconda Enterprise. And also, if you'd be interested in any consulting, training, or support around the data science ecosystem and these open source tools, please reach out to us at ambassador@anaconda.com. Awesome. With that out of the way, let's turn this over now to Q&A. So we got a number of awesome questions. We could have used 50 more people here to try to summarize them. So if we don't get to your question on air or we didn't respond individually, we will get back to you over email. But we will just kick this off without any more ado. So Matt, first question for you. Can I use Dask on my Hadoop cluster, and are there dependencies? You mentioned the Dask Yarn setup project. Can you tell me more about how that works?
Yeah, so it's a good question. It's a very common question. Many people today have a Hadoop or Spark cluster, and they're trying to figure out how to use Dask on that cluster. So your cluster runs something called Yarn, which can be used to deploy Hadoop or Spark or any of a number of other distributed services like Dask. So there's a project called Dask Yarn. I think there's actually now 2 competing implementations of it. And that's a good project to go look at. So I look at, if you go to dask-yarn.readthedocs.io, that'll send information about how to get started. That project is, again, under a little bit of flux. There's an old implementation that works really well. There's a new implementation that works better. So you should also keep up to date on that. But yeah, so it's definitely possible to do. It's commonly done. There's large enterprises that use Dask today on existing Hadoop infrastructure.
Excellent, excellent. That's really helpful. One quick interlude of getting a number of questions. Yes, we will be sharing the slides. Yes, we'll be sharing the presentation materials. You'll have access to all of this. We will send it out to you. All right, back to you, Matt. Next question, and this is another summary question. So I've received a bunch of questions. Does Dask work with X project? And to group them kind of high level with a number of deep learning libraries like Keras and PyTorch, as well as GeoPandas, Xarray, can you give me a little overview of how I would use Dask with some of these existing Python packages?
Right, that's also a very common question. I'll split that a little bit between deep learning and other. So in the deep learning space, so the question is Dask a library for deep learning? It could be, but it's probably not. You'll probably be better served using a library like TensorFlow or PyTorch or any of a number of other deep learning libraries. And those are really designed to do the really core computational piece of deep learning. However, where Dask ends up being helpful is in all of the support around those systems. So often you're doing a lot of data prep, data analysis beforehand. You might also want help setting those things up. Because libraries like TensorFlow and PyTorch all have Python interfaces, they can exist in the same Python process as Dask. And so it's very easy to, with a Dask cluster, load some data, do some data prep. Inside that same Dask cluster, have it automatically spin up for you, a TensorFlow cluster or a PyTorch cluster, and then hand data back and off between those 2 services. This is a very sort of natural process because, again, everyone's living in the same space. You can have 2 distributed systems that are sort of married very, very tightly because everyone's living in the same native memory space with the same Python APIs. It's pretty smooth. There is, I think, in the Dask ML package, there's a bit of utilities to help you set up TensorFlow. That might also be an example to help you see how to sort of move data back and forth. So the other side of that question was, does Dask work with, I think you mentioned GeoPandas or Xarray or other libraries? And the answer to those varies a lot depending on the libraries. Many libraries within the ecosystem have been playing around with Dask. I think the last few weeks I've seen pull requests for libraries like GenSim. Xarray is very, very common. There's a lot of work happening now with scikit-image and scikit-learn. And so those are all sort of works in progress, and sort of different levels of functionality are present in different libraries. So like Xarray has really good support. GeoPandas is like very experimental support. Scikit-learn is somewhere in the middle. So you should go and look at the library you're interested in. Google for scikit-learn Dask, and you'll see some information about that.
Excellent. That's really interesting, Matt. And along those lines, we've now had a few more questions come in about, can we do another Dask webinar? So the answer to that one I can take, yes, indeed we will, and we'll be having a webinar later next month or the month after around machine learning with Dask. So do stay tuned for that. We'll be sure to let everyone know. Matt, another question for you. I've gotten this question along the lines of, you've talked about how does Dask work with X, but how about in terms of the actual machine learning workflow to give us maybe a sneak peek of what we'll see next month? How can I use Dask for my hyperparameter optimization or for picking hyperparameters?
Yeah, so machine learning workflows there's a variety of different ways you can use Dask for machine learning with scikit-learn or other libraries. Hyperparameter search is one way. There's others as well. Maybe I'll just briefly summarize a few different ways. So one, Dask works well with scikit-learn. So we work very closely with that developer team. I'm actually sitting in the same room as many of them right now. We're all off in California sprinting together. So scikit-learn actually already has some parallel systems within it, and we're making it so that Dask can back those systems. So you can use many threads on your computer with scikit-learn in this normal configuration, and you can scale up a number of algorithms, not all of them, but a number of them, automatically with Dask. It's pretty exciting work. So that's maybe one simple way of doing things. However, some algorithms in scikit-learn or other libraries do need to be redesigned. And so we're thinking about how to redesign them, maybe using systems like Dask Array, or using more of the sort of custom code pieces that we've seen in the webinar. We've looked at things like Dask Delayed. So it's a nice sort of, it's a new opportunity to build some new custom algorithms in fun ways. Maybe the third major way of using Dask with machine learning or scikit-learn is to partner with other projects. So in the deep learning question, I mentioned that you can hand data back, you can hand data off to TensorFlow and then hand data back, all in the same processes. That can also be done with libraries like XGBoost or other distributed systems. So again, to summarize that, there's use scikit-learn code and accelerate it directly. That's one option. There's design new algorithms, which may follow the scikit-learn API, but are probably outside of the scikit-learn library itself. And then there's sort of partner or peer with other distributed system machine learning libraries and do maybe just sort of the preparation with them.
Fantastic, Matt. Next question here is, can I use Dask behind my corporate firewall? I noticed you easily spinning up clusters and running distributed computation. So I will take that one. Yes, you can if you buy Anaconda Enterprise. So shameless pitch, come talk to us about Anaconda Enterprise. One of the core features of our enterprise platform is an on-premises mirror of the Anaconda repository, so you can get these packages like Dask behind your corporate firewall. And then in addition, we offer a number of deployment targets for your distributed computation. So if you want to spin up a Kubernetes cluster and install Dask on it and run your computation there, we will support you with that via Anaconda Enterprise. Let's see, another question back to you.
Let me jump in there, Gus, very quickly, just to give it the sort of free and open source bent to that question. So Dask does also support security. It is a secure system. We do things like SSL and TLS. These do require some setup, and so you should use Anaconda Enterprise or some other system to help you. But Dask itself is fairly well hardened, and it's used in a variety of situations where security is paramount. So you can learn a little more about that, again, on the documentation.
Fantastic. Matt, thank you for the clarification there. Much appreciated. One more question back to you. I know we're running a little low on time. Here we go. Is which scikit-learn machine learning algorithms have been parallelized with Dask?
Yeah, that is a long and complex question. There's various corners have been, some corners haven't been. I recommend two things. I recommend that you go to the documentation at dask-ml.readthedocs.io. Or if you just go to the Dask documentation, look for machine learning, it'll be there. And on the side there, you'll see all the algorithms that are currently implemented in scikit-learn. That'll take a little while to get into. There's various corners of the project. I'll also say that this would also be a great, maybe this will be a good question we'll answer next time on the webinar when we talk about this question in the future.
Excellent. And actually, just kidding, one more question. We've mentioned documentation several times. If people want to learn more, we've gotten several questions interested in contributing to the project. Is there a mailing list? Where should people go to either learn more and or actually contribute to Dask?
Yeah, that's a great question. It's an open source project. It's community based. A lot of people work at Anaconda, but many Dask contributors work for other companies or in the community generally. So the documentation is at dask.pydata.org. All of our community decision-making and code review happens on GitHub, github.com/dask/dask. And that's where we have most conversations. So we don't use a mailing list. We just use GitHub. There is a Gitter chat, but we tend to most of the developers hang out on GitHub, and that's the right place to go to. If you have usage questions, I'm curious how this works, help me understand things a little bit, you might also consider asking questions on Stack Overflow, which is where we prefer usage questions to be. And if you tag something with the Dask tag, a number of Dask developers get an email within 15 minutes. So you get pretty good support there.
Excellent. Well, Matt, thank you so much. And for all of you listening, thank you all so much. I really enjoyed the participation we got here. We have a number of questions I'm sorry we don't have time to get to. We will follow up with the presentation materials and an answer to your question. Stay tuned for our next webinar on machine learning with Dask, or scaling machine learning with Dask. And we look forward to seeing all of you then. So once again, Matt, thank you so much. Phenomenal job. And all of you, thank you so much for attending.